In this lesson, we're going to develop our understanding about a very important concept in physics. This is a necessary concept to do physics in two dimensions, but also something we use in one-dimensional physics as well. We're going to talk about the concept of vectors. Now, we've already talked a little bit about what a vector is. We've defined vectors as a mathematical value with a size and direction, and we talked about a couple of values that are scalars. They're not vectors, they're just values. And then their counterparts that are vectors, that are the scalar amount with a direction. So you may remember we talked about how distance and speed are just scalar values. It doesn't matter what direction something is going. When you measure distance, you just accumulate all of the change of position that something goes through as it moves from one place to another. With displacement, on the other hand, you only measure the change in position in a specific direction. The same concept is true when comparing speed to velocity. Speed is just the rate of change in position over time of an object regardless of its direction. Velocity takes direction into account, so you actually only measure the change in position over time in a specific defined direction. That's what makes it a vector instead of a scalar. All right, so you're used to doing this even if you don't realize you're used to working with vectors. Whenever you do basic addition and subtraction problems in math, you're using one-dimensional vectors even if you don't know it. And your brain has gotten so good at doing this because you've done it so much that you think of it completely abstractly without ever taking a vector view of it. I should also point out that in one dimension, we only have two directions, positive and negative. And not all values that are negative can truly be pictured as vectors. For example, when you're dealing with money, there's no money vectors. So if you're working finance problems and you're adding values and subtracting values, when you're subtracting values, usually that's money that you spend or money that you owe. You're not actually talking about an actual direction that you're moving, like to the left or to the right. So it is important to note that not all one-dimensional algebra is vector algebra, but you have done vector algebra before in one dimension, even without thinking about it. For example, if I were to add together these two values, and let's say that these were distances, 2 plus 5, maybe 2 feet and 5 feet, or 2 centimeters and 5 centimeters. How would you go about adding these two numbers together? Well, you're just saying, well, in my head, I know 2 plus 5 is 7. Another way to do it is to put them on a number line, which allows me to draw one-dimensional vectors and add them together. Here's my origin, my 2 vector, and my 5 vector. Notice that I'm starting the 5 vector where the 2 vector ends, and both of these are pointing to the right because they're both positive. Now, to get my resulting sum vector, I'm just going to draw a vector that starts at the beginning of the first and goes to the end of the second, and that's going to be my 7 vector. 2 plus 5 equals 7. To state this problem in words, since 2 plus 5 equals 7, the quantity can be represented either with a 2 vector and a 5 vector, okay? And I'm just going to use the word unit because we're measuring these in some unit. I mentioned it before, centimeters or feet or meters or something. So I have a 2 unit vector and a 5 unit vector, or because of that equivalence that is there, 2 plus 5 equals, I could just represent it with a single 7 unit vector. But no matter what, that vector has to be pointing to the right. In fact, all of my vectors in this case are pointing to the right. Now, why make such a big deal about how 2 plus 5 equals 7? Well, it's going to be an important concept in using two-dimensional math with vectors. So make sure you hang on to that concept. In fact, I'm going to be repeating it a few times on this slide. What about this problem? 5 minus 2. Well, what would that look like? A minus vector is just one that goes in the opposite direction of the positive vectors. So here I'm going to have my 5 vector first, starting from the origin, but then a minus 2 vector, which starts at the end of the first again, but it goes backwards. It goes to the left 2 units. My resulting sum is then going to connect 0 to the end of that minus 2 vector. I'm going to have a sum of 3. And once again, 5 minus 2 is the same as 5 plus negative 2. Okay, so I'm just adding vectors like I was before. There's nothing special about subtraction. Subtraction is just adding the negative. And I can represent that with a 5-unit vector and a negative 2-unit vector, which is simply a 2-unit vector pointing the opposite direction, to the left. And then the result is one 3-unit vector pointing to the right. So you knew 5 minus 2 was 3, but this is just another way of thinking through why 5 minus 2 equals 3 in the terms of vectors. And this should be pretty obvious to you. This should make a lot of sense. Let's take a look at another one of these. What happens if I have 2 minus 5? Can you pick out what's different about this one that makes it a significant example? So I'm going to start at my origin and draw my 2 vector. But now I have, the negative 5 vector that I need to add to this. That's going to take me to the left of the origin. So my resulting sum vector is actually going to start at the origin and point to the left. That makes it negative. And in this case, 2 minus 5, again, is 2 plus negative 5, which is represented with a 2-unit vector to the right and a 5-unit vector to the left, or a negative 5-unit vector. Or I can represent it with a negative 3-unit vector. And because it's negative, that means that vector is going to be pointing to the left. All right, now let's take a look at another similar problem. What if I have negative 5 plus 2? Now you can pick out why this problem is the same as the previous one. I've just reversed the order. Do you remember the property that says that I can add numbers in any order and still get the same value? Well, that's what I'm going to explore here in terms of vectors. So I'm going to start at the origin again, and this time I'm going to draw my negative 5-unit vector first. So it's going to go to the left. Then I'm going to add to that a 2-unit vector that's going to start at the end of the first one and go to the right. Am I going to end with the same result as previously? Well, yes. When I start from the origin and draw to the end of the second vector, I find that I have a 3-unit vector to the left, or a negative 3-unit vector. This is the commutative property, and the commutative property applies to vector math in 1 and 2 dimensions the same way that it works for adding and subtracting in algebra. Okay, so again, I can show this as a negative 5-unit vector pointing to the left and a 2-unit vector pointing to the right, or a single vector pointing to the left, a negative 3-unit vector. An important pattern from this slide, it's important for you to keep in mind that when you state an equivalence, you can represent the value by either the statement on the left of the equal sign or the statement on the right of the equal sign. The reason that's important is because in physics, we're going to be dealing with some vectors that are pointing in directions where we can't really use them directly in the direction that they're pointing. So we actually need to restate those vectors in terms of other vectors that add up to the same amount. They're equal, and therefore we can express them in equivalent terms. All right, so those are one-dimensional vector problems. In basic physics, we're regularly going to encounter two-dimensional vector problems, where we have something pointing in a direction that's not just on the number line. It's going to be pointing in a direction that deviates from the horizontal. So let's take a look at an example of this. Here I'm going to have a vector that has a size. In this case, the size of this vector, the magnitude is 2. That 2 is always going to have a label to it. I need to know 2 what? What are my units? In this case, it's going to be 2 meters. So this is a displacement vector because it's measuring the change in position of an object. Now, before we move on, I just want to point out some of you are looking at this and saying, hey, this is a graph. And I recognize that on the x-axis, there's going to be something like time, and then position is going to be on the y-axis. But don't get confused. When we draw out vectors, we always draw them on maps, not graphs. What is a map compared to a graph? Well, a map is a special type of graph where the x and y axes are actually the same units. So my x-axis is position and my y-axis is position. It's just different kinds of position, vertical versus horizontal position. And then we're mapping out exactly where the object is moving. Maps don't always have to be displacement and position maps, though. We can also draw maps of velocities that have velocity on the x and the y-axis. So just keep in mind that this is not a graph. We're not measuring the change in position over time. We're just looking at where this object is actually moving in 2 dimensions. It's actually going from a starting place and then moving 2 meters in some direction that's not just along the horizontal or just along the vertical. it's two-dimensional. It's got horizontal and vertical built into it. And that's the other important point, is that it has a direction. The angle direction of this vector is 30 degrees. Just want to point out that the angle in my sketch, the actual angle, probably doesn't measure 30 degrees. I didn't make sure that when I drew that angle that it was exactly 30 degrees. And the reason for that is because it's just a sketch. It's just a model that I'm using to help me visualize the problem. But it doesn't have to be exact. Now, I'm not doing math with this vector yet, but if I was going to be doing actual math with this vector, one way I could approach this is by getting a protractor and a ruler and very carefully drawing out every vector on graph paper in the exact angle and with the exact to scale lengths that the vector should be represented by. And then by doing that, as I do math with this vector, I can measure the resulting vector and measure it to scale the same way that I drew everything to scale. And by measuring it very precisely, I could figure out what its length was without ever having to use any algebra or any trigonometry. Instead of doing that, we're going to be drawing models and sketches, and then we're just going to use trigonometry to solve for unknown values. We're going to be doing the math instead of drawing things out exactly. And that's why it doesn't really matter if my sketches are exact. They're just sketches and models that I'm going to be using to represent things for now, so I can actually use math to solve later. So if vectors have size and direction, I need a way of noting both of those values when I express the vector. So the way that I would write out this vector and describe it is by saying it's a 2-meter vector at 30 degrees. And when I write out that 30 degrees value, I'm always measuring degrees from the positive x-axis counterclockwise. Okay, so I'm starting at x and then going upwards counterclockwise 30 degrees. That's the value that I'm going to report. To add vectors together, I'm going to do what I did on the previous slide in one dimension, except now we're going to do it two-dimensionally. So if you're adding two vectors to find the resultant, that's the name of the sum of vectors. It's called a resultant vector. The first thing you're going to do is draw your first vector starting at the origin on your map. You have to choose an arbitrary 0, 0 point on your map somewhere that you're going to start drawing your vector. And again, just like with reference point in kinematics, this is an arbitrary choice you get to make. Your vector can go anywhere on your map. You're going to draw your second vector that you're adding together to find the sum, starting with its tail on the exact head point of the first vector. So your next vector is going to start where your first vector left off. And you notice I did that in one dimension when I was adding together those one-dimensional vectors. Then you're going to continue drawing each vector. So if you have multiples, you could have 3, 4, 5, 6, however many vectors. You're going to continue drawing each vector starting with its tail at the head of the previous one. And then when you've finally drawn all of your vectors, tail to head and then tail to head, the last thing that you're going to do is draw a resultant vector that starts at your origin at the tail of the first vector and then goes to the head of your final vector. And again, that's what I did in one dimensions. When I found the sum of those values, I always drew a vector from the origin, that's the start of the first vector, to the end of the final vector to get what the result was, or the sum. A very common thing to do when working two-dimensional vector problems is to find the set of vectors that are at a right angle to one another that add up to your angle vector. Okay, so here I have a 2-meter vector at 30 degrees. I could find a set of vectors that I can add together that are at a right angle to each other. It's going to make this into a right triangle problem. And if I add together x plus y with basic vector math, that's going to equal 2 meters at 30 degrees. Just want to remind you of a concept we talked about previously in this lesson, where we could represent an equivalence by the expression on either side of the equal sign. The same is true with vectors. I could express this vector as 2 meters at 30 degrees, or I could represent it as the sum of the vector x plus the vector y. X is my vector along the x-axis, which is very convenient because it's all horizontal, and y is my vertical vector that also is convenient because it's entirely vertical. But how am I going to go about figuring out the values of x and y? Well, I'm going to have to use trigonometric functions, sine, cosine, tangent. And in order to do that, I need to be able to recognize some relationships in this right triangle. And this is only going to work if I have a right triangle set of vectors. But the good news is, remember, I can add together any set of vectors to equal my resultant. So I'm just going to choose vectors that make a right triangle because that's the kind of triangle that I can do math with. In this triangle that I have here, X represents the side adjacent to my known angle as long as I know that bottom angle of my right triangle. Y represents the side opposite, and H in this general triangle is the hypotenuse. And I'm going to be using sine, cosine, and tangent functions in order to figure out unknown sines and or unknown angles in vectors. So if I look at these three functions, I just want to remind you how these work. The reason these trig functions work is because right triangles have fixed ratios of side lengths depending on the angles within the right triangle. So that base angle that I have there, that theta, whatever that theta is going to determine the ratio of y to h, y to x, or x to h. And that's what I'm using. That's the theory behind these trig functions. So like, let's say my theta is 30 degrees. It's 30 degrees in the triangle in the lower left. There is a specific ratio of y, h, and x. And when I run the sine of theta, it's going to tell me what the ratio is between y and h. And I'm going to be able to use that ratio then to calculate what the unknown side is. In this case, I know the length of the hypotenuse is 2 meters. So when I punch the sine of theta into a calculator, the sine of 30 degrees, my calculator is going to give me a fractional value, and then I can use that with my known hypotenuse to calculate the other value just using basic algebra. One important thing to consider here, you do need to make sure that your calculator is set to degree mode when using degrees. And later in physics, we're going to be using radians to measure angles. You'll need to be in radian mode when measuring in radians. Your calculator will only give you the correct ratio if you have it in the correct mode. And then the other thing to remember is SOHCAHTOA. Sine is opposite over hypotenuse. That's the angle opposite the known angle divided by hypotenuse. The cosine is the adjacent side divided by the hypotenuse. And tangent is opposite over adjacent. Tangent is the function you use if you don't know the hypotenuse, but you know the other two sides of your right triangle. Okay, so which one are we going to use to figure out the unknown sides in our right triangle at the bottom left? Well, let's see if we can figure out the x side first, the horizontal. To do that, I'm going to use the cosine function because that's the adjacent side. And that cosine ratio that my calculator returns for 30 degrees is going to be equal to the ratio of the adjacent side, x, over the hypotenuse. Or I can simplify this by saying that x is going to be 2 times the cosine of 30 degrees. You're going to find that if you know the bottom angle of your triangle, that sine and cosine are very easy to use because if you know the bottom angle, your unknown value is going to be the hypotenuse times the trig function applied to your angle. So 2 times the cosine of 30, we'll just record the value at the bottom. It's 1.73 meters. And then for sine, it's going to be the same thing. I know the bottom angle. So when I plug in opposite over hypotenuse, it's going to be y over 2 meters. I need to multiply both sides by 2 to get y on a side by itself. It's just going to be 2 times the sine of 30. My hypotenuse length times the trig function applied to the angle. And 2 times the sine of 30 is going to be 1. Now, you may have seen this coming because this is a special type of triangle. A 30, 60, 90 triangle has side length ratios 1, 2, square root of 3. And I didn't have to know that relationship. I can just use the cosine and sine functions in order to figure out what these sides are going to be. But these are the vectors that add up to a 2 meter vector at 30 degrees. I would have to have a 1.73 meter vector to the right and a 1 meter vector vertically pointing upward. Another important point about vector math is that it is commutative, as we mentioned before.
What does that mean? That means that I can add together my addend vectors in any order to get my resultant vector. So here, again, I have this 1.73 meter vector at 0 degrees, or to the right, and a 1 meter vector at 90 degrees, or straight up, add together to make a 2 meter vector at 30 degrees. What would happen if I added those vectors in the other order? What if I added my vertical vector first? Well, look, it's going to add up to the same resultant. I'm going to move my vertical vector over to the left. That's going to be the first one, starting from the origin. And now I have to start my horizontal vector at the head of the first. Notice that it ends at the same place, and I'm going to have the same resultant. It's still 2 meters at 30 degrees. I also want to point out that this interior angle in my triangle is 30 degrees as well. Get used to recognizing alternate interior angles like this, because being able to recognize these will help you to solve vector problems. We're going to see another instance of an alternate interior angle by the end of this lesson. There are two major types of vector problems we run into in physics, and usually these vector problems aren't like the whole problem. They're just a part of doing the problem solving for a larger problem. We just did the first type of vector problem where we were given a vector and we needed to find the x and y components. And then if this were an actual physics problem that we were solving, we would use those x and y components for something that we were doing. The other type of vector problem is when we're asked to add 2 or more vectors together and find the resultant. Now, this first type of vector problem is very important for kinematics. The second type of vector problem is important for other types of physics, especially when we get into collisions and momentum. Let's take a look at one of those second types of vector problems. So consider this. As it cleans an area in a room, a robotic vacuum cleaner moves the following distances and directions. So we've got some displacements here. 2 meters at 30 degrees, that's the one that we just did. 3 meters at 315 degrees, then 1 meter at 180 degrees. What is its ending displacement, its resultant displacement after moving all of these different ways? Do you see that this is the second type of vector problem where we're going to be adding 2 or more vectors to find a resultant displacement? And because I've already worked out the math on the first vector, I'm just going to keep that and make that the starting vector for my problem. So I've got the robotic vacuum cleaner moving 2 meters at 30 degrees. The next vector is going to be 3 meters at 315 degrees. Ooh, that's all the way around in quadrant 4 of a coordinate plane. So that's going to look something like this. Notice that I started it at the head of my first vector. Now I know that since 270 degrees points straight downward, 315 degrees is 45 degrees past that. That means that this angle has to be 45 degrees because the angle from this vector to the negative vertical is also 45 degrees. And you have to do a lot of thinking like that when you work out and draw out these vector problems. As you make your sketches, make sure you're thinking about what are the angles that you know based on what's given in the problem. What are the angles that are actually going to be useful to you? And then lastly, I have a 1 meter vector at 180 degrees, but that's just a vector pointing directly to the left. So I don't have to write down any angle values associated with it. It doesn't have an angle from the horizontal. So that's easy for me to note here. And then I'm going to draw in my resultant vector. Now, I don't know what my length or direction of my resultant vector is. That's what I'm trying to find. How am I going to find that from the information that's given? Well, if I break all of these vectors into x and y vectors, like I did with that first one, I should be able to figure out what the x and y components of the resultant are. So let's just take a look at this vector on the right. That's going to break down to an x and a y, and I should be able to figure out those values. How am I going to figure out what x and y are for this triangle? Well, there's a couple of approaches to this. First of all, I can observe that this is a 45, 45, 90 triangle, so I know the sides are going to have length ratios of 1, 1, square root of 2, knowing my special triangles. Even if I didn't know that, though, I could use sine, cosine, tangent relationships, those trig functions, to figure out what the unknown side lengths are. That's the approach that I'm going to take. I'm just going to note that because this is the isosceles right triangle, my sine value is going to equal my cosine value. And even if I didn't know that going in, when I punch it into my calculator, it would just give me the same value and I would solve the same thing. So if I use that relationship, I can observe that, if I'm just going to use sine here, that y side that I don't know is going to be 3 times the sine of 45. And because the sine of 45 is equal to the cosine of 45 for a 1, 1 square root of 2 triangle, that means that the x value is going to be 3 times the cosine of 45. When I plug this in and solve, I find that y2 and x2 equal 2.12 meters. So I'm just going to go ahead and replace those values in my diagram. Those are going to have the same side lengths because of the special type of triangle this is. All right, and then now that I know all of this data around the outside of this problem, you can kind of see that I'm forming this rectangle. Not all of these are going to form these nice rectangle shapes, but many of them will. Can I figure out what the unknown sides of that final triangle, my resultant vector, in this rectangle shape are? Well, I sure can. And you could do this multiple different ways. I'm going to do it the official way that we work with vectors, and that is to add up all of the x side lengths and all of the y vector component lengths, and that should give me the x and y component lengths for my resultant. So let's start by adding up the x's. I have a 1.73 meter x length, a 2.12 meter x length, and then that other x length goes backwards to the left 1 meter, so I'm going to have to include that as a -1. Okay, so I just added together all of the x lengths. Notice that that's going to give me the x value for the resultant. It's going to give me that x vector in the lower left. I'm going to do the same thing with the y's. I go up 1 meter for my first vector, then down 2.12 meters, or -2.12 for my second vector, and then my third vector doesn't have a y component at all. It's entirely horizontal. So I'm just going to note that that's 0 meters from the third vector. When I add these all together, I find that my total x value is 2.85 meters, and my total y value is -1.12 meters. I'm just going to go ahead and put these values into my diagram. For that -1.12, I'm just going to include it as 1.12, but downward instead of upward. And those are the components of my resultant. Now, if I know the components of my resultant, can I figure out the value of my resultant? Remember, the value of a vector has to have a magnitude and a direction. Well, let's start with direction. How am I going to figure out what the angle of this is? I need this angle here from the horizontal or its complement. And in fact, in this case, because I'm measuring from the positive x-axis counterclockwise, it would be a lot more helpful to have the complement of this angle. And we'll get there eventually, but I'm just going to use that alternate interior relationship again and just note one of the inside angles that I can measure is this one. And just like a lot of physics problems, there's multiple ways that you can do this. You could go directly for that complement angle instead of ever worrying about measuring either of these alternate interior angles. The reason I'm measuring the alternate interior angle is because I like to consistently measure the bottom angle of a right triangle, and that way my opposite and adjacent sides are always the same x and y. However, if you're comfortable changing and doing different sides and not always having x and y be the same sides of your right triangle when looking from the bottom angle, you can feel free to solve this however you like. However, my personal recommendation is to always measure the bottom angle of a right triangle and just consistently keep x and y in the same place. That doesn't work for all problem types, so maybe it does make sense to mix it up and try some different things. That's just the way I'm going to be doing this one. So I'm going to be looking for that angle theta r, the theta for my resultant. And I'm just going to note that the tangent of that theta r is y over x, opposite over adjacent. Okay, and I know my opposite value is 1.12, and my adjacent value is 2.85. And when I divide those two, I get 0.393. And actually, when I punch this into my calculator, I'm going to keep all of the decimal places after that when I run the next function, because the inverse trig functions are very sensitive to rounding error. So I want to make sure that I keep as much of this value as I can in my calculator and not actually round it off to 0.393. Okay, so how am I going to get theta on a side by itself if I have it as the tangent of theta? Well, if I take the inverse tangent or the arctangent, same thing, of both sides of this equation, the inverse tangent of the tangent of theta, the inverse tangent undoes the tangent. So instead of having the inverse tangent of the tangent of theta, I just have theta. And then on the right side, I have the inverse tangent of 0.393, and that's a function that I can plug into a calculator. And when I do that, I find that theta of the resultant is the inverse tangent of 0.393 or 21.5 degrees. So I can go ahead and replace theta r in my drawing with 21.5 degrees. I know that that's the same theta as my alternate interior angle, but the angle that I'm most concerned about is the top angle of my triangle. And I can figure out that one by considering that it has to be the complement of 21.5 degrees for a couple reasons. So I know it has to be 69.5 degrees. And honestly, that's not even the full angle that I'm interested in, because I need to report the angle from the positive x-axis counterclockwise. So I have to add in these extra 270 degrees as well. So it's going to be 270 degrees to the downward axis, the downward y-axis, plus an additional 69.5 degrees. That entire angle is going to be 339.5 degrees, and that's going to be the angle of my vector. But that's only one of the pieces of information I need. I also need the length, the magnitude of the vector. And to find that, I'm just going to use a squared plus b squared equals c squared Pythagorean theorem. So when I solve this, it's going to be c equal to the square root of 1.12 squared plus 2.85 squared, or 3.06 meters. And my final report for the magnitude and direction of this vector is going to look like this: 3.06 meters at 339.5 degrees. That's how I would state the final displacement of this robotic vacuum cleaner in vector form. Now, these sorts of problems where we are measuring displacements are very concrete. We're used to considering changes of positions in certain directions in the real world. But what about a problem that's a little more abstract, like this one? During takeoff, a jet's engines propel it forward at a rate of 247 kilometers per hour with respect to the air at an angle of 11.5 degrees above the horizontal. Now, to think about this, it's as if the jet is pushing air backwards at 247 kilometers per hour directly behind it. Keep in mind, the jet is pointed upward at an angle, and so are the engines. So it's pushing this air diagonally downward and propelling itself diagonally upward. What if we add in another factor here? The wind is blowing horizontally along the ground and toward the front of the plane at 24 kilometers per hour. So this is a headwind parallel to the ground. So it's going to be blowing toward the nose of the plane, but at an angle to the diagonal takeoff motion of the plane. The question is going to be, during takeoff, what is the velocity of the plane with respect to the ground, taking into account this wind that's blowing? Now, of the two types of vector problems, I think you can identify that this is the second type. I'm going to be adding two vectors together to get a resultant. And this one's a lot more difficult to visualize than the robotic vacuum problem, because we're talking about velocity vectors instead of displacement vectors. So it's a little bit more abstract. Let's make a diagram to help us visualize what's happening here. So here's my airplane, and this is the effect of the engines. The engines are pushing it forward with a velocity of 247 kilometers per hour with respect to the air. but the air is actually moving with respect to the ground. It's moving at a rate of 24 kilometers per hour toward the nose of the plane and parallel to the ground. So the resulting speed of the plane isn't going to be 247 kilometers per hour with respect to the ground at 11.5 degrees. It's going to be a steeper angle than 11.5 degrees and a slower velocity, probably. At least according to this diagram, it looks like it's going to be slower. So how am I going to figure this out? Well, I'm going to use the same techniques that we used in the previous problem. I'm going to use trig functions to figure out what the components are in this problem. My first vector is going to have an x velocity and a y velocity component. And then the resultant vector is going to have an x and a y component. And I should be able to figure out what these components are. To figure out the components of my first vector, I'm just going to use those trig functions. The x component is going to be 247 times the cosine of 11.5. And again, I got this from using the cosine formula. The cosine of theta equals the adjacent over the hypotenuse. And because I know the bottom angle, it's going to be that the x side is equal to the hypotenuse times the cosine of theta. 247 times the cosine of 11.5. That's 242 kilometers per hour. Now let's just consider, that's only 5 kilometers per hour shorter than my other vector of 247. Could that be right? Are these two vectors going to be almost the same length? Well, 11.5 is not a very steep angle. So I would expect that my adjacent side is going to be very long and my opposite side is going to be very short. So if I calculate the length of that opposite side using the same technique except this time with sine, I'm going to find that the opposite side is 49.2 kilometers per hour. I'm going to go ahead and replace those velocity variables in my diagram down below with the calculated values that I just found using trig functions. Now I can figure out what the y component and x component of my resultant are using that technique that I used before where I add together my x's and my y's. And again, do this however you prefer. I prefer to use this technique because it helps me keep my variables straight. So in the x dimension, I have 242 kilometers per hour from my first vector and negative 24 kilometers per hour from that second vector that's pointing directly at 180 degrees. In the y dimension, I have 49.2 kilometers per hour from my first vector, and that's the only y dimension vector. The horizontal vector doesn't have a y component. When I add these together, I find that the x component of my resultant is 218 kilometers per hour, and the y component is just going to be that same 49.2 kilometers per hour. And then I can go ahead and plug these in on the diagram and use my trig functions to solve. First, I should figure out what my unknown angle is. I have this theta that's going to be the one that I want to measure. This is the angle above the horizontal. This is above the positive x-axis. But I can't get this one directly because it's not in my triangle. So I'm going to have to use that alternate interior angles relationship and note that this is the same angle. And this is inside the triangle. So this is a good angle for me to know. And then I'm going to note that I know the opposite and adjacent sides. So I can use the tangent relationship to solve. The tangent of theta is opposite over adjacent, or 49.2 over 218, which is about 0.226. And again, I'm keeping this entire value in my calculator. I'm not just rounding off the 3 decimal places. I'm going to take the inverse tangent of both sides. So the inverse tangent of that value 0.226 and then the other decimals behind it, that gives me a value of 12.7 degrees. And I know that that's the 12.7 degrees inside my triangle and below my triangle in the diagram. And then I'm going to calculate the length of VR because I need both magnitude and direction. So I'm going to use the Pythagorean theorem with the values that I know to calculate that the resulting velocity of 223 kilometers per hour. And to report my final vector, I'm going to have to report both that magnitude and direction, 223 kilometers per hour at 12.7 degrees. So now you know a bit more about vector math. This is going to be a very important tool for us to use to solve any problem in 2 dimensions in physics.